We'd now like to calculate the electromotive force in a loop that we know we can calculate by calculating the change of magnetic flux. So what we have here is a wire loop, and I'm going to pull this wire loop at a constant speed with a pulling force. And that wire loop is going to be located in a region where there is a non-zero magnetic field. And let's direct that magnetic field like this. And out here, B is 0. And I want to calculate the induced current that flows in this loop by calculating the electromotive force. And then I'll set that electromotive force equal to the induced current times the resistance. Now you can see that when I pull this loop out in this direction, that I'm going into a region of zero magnetic field, so I'll be losing a little magnetic flux. One way to kind of illustrate that is to draw the loop at a slightly later time. I'll exaggerate it. So what's happened is I've lost this amount of magnetic flux because in this region, B is 0. And if my loop is a height h, and I'm pulling it at a constant speed, that in a time delta t, this distance here is just v times delta t. And so I now want to calculate the change in magnetic flux. Now, of course, depends on how I choose my surface. So I'm going to choose my unit normal out of the plane of the figure. And so the dot product of B with that unit normal is positive. And the change in magnetic flux, it's decreasing because this flux, as I move the loop, is being lost. And it's being decreasing by the amount of the B field. Here we're assuming B is uniform times the area of this little patch strip, V delta T H. And my electromotive force is minus the change in flux divided by the time. And in the limit, that's a derivative. And so I simply get minus two minus signs, so I have a plus VH. And so the induced current is equal to the electromotive force divided by the resistance. And that's B VH divided by the resistance. Now, notice that this is a positive quantity. And if I choose this circulation direction in that way, then I'm circulating like this. This is my circulation direction. I have to be careful here. Think about this for a second. Actually, my circulation direction is like that. And because that's consistent with my right-hand rule, and because I have a positive flux, that tells me my induced current, positive not flux but EMF, that tells me that my induced current is going in that direction. And that tells me that my induced field, B induced, is in that direction. And that agrees with what we expect because the magnetic flux through this loop is coming out of the plane of the figure and decreasing. And so we need more induced flux coming out of the plane according to Lenz's law. Now, there's more that we can say because let's notice now that in my loop, so I'm going to draw that loop again. I'm pulling the loop V, and there's an induced current in a magnetic field on this side. So let's now do a calculation, I, j hat, k hat. Well, I know that there's an induced force which is equal to I induced, we'll call the vector H, pointing down, so H is in the direction of the induced current, cross the magnetic field, and so I get I induced. H is the length H in the minus j hat direction. I'm crossing that B in the positive k hat direction, and j hat cross k hat is I hat with a minus sign. So what I'm getting is an induced force is equal to I induced HB in the minus I hat direction. And I've calculated this induced quantity. And so I get a V. I'll get a B squared. I'll get an H squared. And I divide by R in the minus I hat direction. Now, if I want to pull this loop at a constant speed, then my pulling force has to be equal to minus the induced force, which is in the negative I hat direction. And so I have to pull this if I want to go at a speed v with a force equal to v b squared h squared over r. Now I'm putting energy into this system, and recall power is Fp dot v. So the velocity is in the I hat direction, and I get v squared b squared h squared over r. Now, if I can rewrite this, notice that I is b v h over r, but I have a quantity v squared b squared h squared, so it's easy to see that this is I squared times r. Square this. You have to multiply by an r to get that. And that is the power that I need to put into the system. Where is that power going? Well, this is what we call Joule heating. And so as I pull this loop, an induced current flows, and the induced current, the wire will heat up, and that energy will be dissipated thermally at the rate I squared over r. And that's what we expect.